Hi, my name is Charnmanee, and today I'm going to present on a paper called Gait Transition for Quasi-Static Hexapedal Locomotion on Level Ground. I know that is actually a lot of big words. So let me explain a bit. The gait transition actually refers to movement of robots, as in like permutation of movement, different type of movements, which I'll be talking about later on as a big part of the paper, gait complex. And yes, as the authors has highlight level ground. So what is this paper about? This paper introduced a new way of formalizing or coordinating with periodic tasks for gait transition, such as a new way to actually move or dictate the movement or plan the movement of the robots using topological space in terms of gait complex, which represents different permutations, cyclical permutation of the robots and legs. And how do they do it? They actually make a very smart use of classical group theory to represent the what people usually do nowadays, which is the algorithm to move normal robots, the combinatorial search and optimization. But then, so why is that important? It is important because the method that the authors is actually employing is actually a lot more actually simple than the combinatorial search and optimization. So essentially, it's combining the two thing called which I will explain later, a stance complex and a gait complex to actually limit and control the motion of the robots. Okay, so how do they do it? They usually, the author decompose the space of periodic gaits into cellular complex and index using Young tableau, which refer to table in French. Yes. So essentially, they make a gait complex which represents all the moves that the robots can do with different legs, and then label them with the Young tableau. And then there's construct an additional complex, which is called a stand complex, that actually talks about, actually gives value within about the stability of the robots. So assuming if you have a robot, which I will show you a video, it's called this robot Rex.
Black.
Sure. So why is the stance complex important? So here's the legs, and here's the plane. So assuming if you have a rock on the robot and you want to travel along this way, then the stance may not be super important, as you can move with 2 legs or 1 leg or whatever the stance. So the stability requirement is not that important. However, assuming if you don't have a rock, but you have, as Professor Robinson said, a cup of coffee. Yes. So the stability of the robot, which should actually be very crucial in this case, because you don't spill coffee, the mission would fail.
Coffee mission.
Right. Next point. So I'm gonna show you a video of what the robot actually looks like. Pretty cool, by the way.
Here's the robot. Cool. Yeah, it's pretty scary. It's like a bug.
Notice the way it moves. It uses 2 legs and 1 on the other side, and they alternate the movement pattern.
Just to give you an idea of scale, it's about this big.
Level ground.
It's like a happy frog.
And then pretty cool. you can travel over a big obstacle, such as a rock. I think the reason the author didn't actually explain this, but the reason that in the video the author uses movement with 2 legs and 1 leg on the other side to actually provide the robot with good stability, also with good speeds.
It's on top of the engineering building, by the way.
So as you can see, the robot can actually flip. So it doesn't matter whether the robot cannot go the other way. It can flip, or if it falls, flip over, it can travel the other way. Yeah, this is the good part.
Oh.
Yeah, okay.
You didn't have any of the
Just
pictures.
want to show that one.
Yeah?
Thank you. So the stance complex, as you can see, this is a stance complex of 3 leg robots, and the area right here represents the movement where you need to move 3 legs at once, and that's not very good to the stability of robots, because you want the robot to be more stable. And how do you make the robot stable? You move each individual legs at a time. That actually provides the robot with the most stability overall. So yeah, so the idea is that these stance complex actually show the space in which
What are the axes?
yeah, so the tolerance with the axes. Okay, moving on. So this is supposed to be a stance complex cell for 4 legs, robot 4 legs. So as you can see, stance 0, assuming 4 legs, you have the stance that has the best stability is actually a stance where all the 4 legs are attached to the ground, and vice versa. Yeah, if you don't have any leg attached to the ground, then yeah, the stability not so much. Yeah, and then it alters between. So if you actually want to maximize speed, you may want to give up some of the stability, sacrifice some, and perform one of these stances, and transition to gait complex. Yeah. Okay, so let me explain a little bit of Young tableau. So this thing right here is called Young tableau, which is supposed to be the curl for the tableau. And yeah, so this one doesn't care about the order. And this one is actually a representation of legs. So let me explain. Here, this means the robot is actually moving 3 legs at once, 4, 1, 3, and then it moves 2 after a period. So as you can see, if you're going to map this, it's going to be a 1-dimensional stuff. Okay, so you kind of get the basic idea, right? Okay, this is the gait complex of 3 legs robots. So before I do that, let me explain to you, use black, I guess, a normal torus of human locomotion. So that this point right here can be represented as 1, 2, of course, because we only have 2 legs. And yeah, we can call that a hop. And notice the hop, you perform a hop and you don't have any more period between different legs. So represented by single dots. However, you can do 1 and 2 movement. So you move using, so 1 is the left legs, and 2 denotes the right leg. You move left, and then you do a right. But the period that you do left, you can do left, right, and you can do faster and faster with different periods. So yeah, it represents the whole ring right here, the line, making a 1D torus. 1D. So assuming if this point, you can assume that the period is actually something like 1, 2. But over here, you can move so fast that it looks as if it becomes 2 and 1. So let's imagine assuming if you turn on a fan and it starts spinning. At one point, when the speed gets fast enough, it looks as if the fan's moving backward the other way, right? It's spinning the other way. Kind of like the same thing. That's the basic idea for the
The basic idea is this is repeated.
Yes. And now, yeah, let's move on to the torus
It's fun.
for the gate complex. Yeah, kind of messy. And this is red. Yeah. Okay, let me explain a little. So this one's supposed to be red, the area. So prompting for the 3 legs robots can be something like 1, 2, and 3, right here. A point. This one's going to refer to movement of 1, 2, and 3. And then this area can be something like 1, 2, and 3. Notice it's 2-dimensional area. And this refer to 1, 3, and 2, which is 2-dimensional. So the torus represents the 2-dimensional areas, and as you can see, it goes all around. And lastly, it could be, yeah. Want to explain lastly about the gate complex for 4 legs. So this is actually the most interesting parts. So assuming you're facing me this way, and I label this point to be the prompting, right there, 1, 2, 3, 4. And yes, so a face, this one would represent something with 2-dimensional movement, something like 1, 3, 2, and 4, or 1, 3, 4, and 2. So it has 2 periods. So refer to 2-dimensional. The edges refer to something like 1, 3, 2, and 4 with 1 period in between. And lastly, the area inside, which I kind of dissect. So if you look at this way, you can see one area here, here, and last area here. So that's 3. But assuming if you have like 2, 1, and 6 right here, it will be 6 areas, which represents cyclic permutation of rippling, which is robot walking with 1 leg at a time, 1, 2, 3, 4, and like all the cyclic permutation. And that's it.
Questions? So what is the topology value? What's good about building this gate complex? Why would you want to do that?
I mean, if you want to design a robot, you want to know like what all the moves you can do, and then you want to, assuming if you the robot of course has accelerometer and sensory module, so that you can combine the gate complex, something like this, and the stance complex, and assuming if you program the robot and you want the robot to move over obstacles, something like a big rocks, it can calculate whether within the task, like which way or which type of movement within its gate complex it should deploy to balance between the speed you want or the stability. So it's actually a good way to actually, it's actually deeply, it's a good way to understand the movement. It's a display total space movement of the robots.
So So given that graph earlier with I think it was just the 4 legs, which is the most stable gait and which is the fastest? And was Rex optimized?
I mean, the fastest one is probably trotting, which is assuming this is leg 1, the front left, and front right is 3, and on the left side, the back leg is 2. So it's 1, 2, 3, and 4. The fastest one is trotting, of course. So it's kind of like Rex, but Rex has 6 legs, and trotting like that probably not as stable as the movement shown in the video where you do 2 legs at once and alternate with 1 leg. And,
So what actually dictates the shape of our abstract simplicial complex? Is it completely arbitrary? So it's like is that, yeah, that's pretty much it. Like
the shapes?
Well, like the shapes, or what kind of faces we have, what kind of simplices we have. Like what dictates, for example, a 3-face. Like if I were to have a 3-simplex in my simplicial complex, what would that represent? What would that represent for a gait complex?
You mean the area of like 3 dimension?
Yeah. So like
yeah. Also, something like this has 1 dimension, right? Assuming you move leg 1 first, you stand, and then you have a period between moving the first leg and second leg. That is the transition between the movement. That is representing 1 dimension. So if you have something like a 3D within like a gait complex, something like this, meaning it has movement consists of 4 legs at different times. So if you imagine you have 4 legs, yeah, so you should have 3 different slots between. Right.
So would an n simplex be would an n simplex would correspond to the n period? So like if I had 3 sort of breaks, I would be a 3 simplex. If I had 4 period breaks, I'd be a 4 simplex.
Right.
Okay.
Yeah. The tricky thing is like that's the reason why the author did not use the representation in like 3D diagram, 2D of course, because assuming you have like legs which has 6 legs and you want to move 6 legs 1 at a time, you need which has like 5 breaks in between, and like you cannot represent it in in form like 3D or something.
No, I was just curious.
Yeah.
Okay.
So all of the spaces are toruses.
Right.
They're all
Okay.
toruses because they're basically, the legs are executing periodic motion.
Okay.
And so these are delta complex decompositions of the torus.
Okay. All right.
Yep. All right. Any other questions? Great. All right.